Welcome to week 6, lecture 26. In week 5, we have started our discussion on pressure measuring instruments, and during week 5, we have talked about measurement of moderate pressure as well as measurement of high pressure. So, in week 6, we will talk about measurement of high vacuum or measurement of very low pressures. So, now we have talked about bellows, Bourdon tubes, diaphragm gauges. If you visit any chemical process industry, you will find that lot of pressure gauges are made of bellows, Bourdon tubes and diaphragm gauges. One reason may be that most of the operations will take place at moderate pressures. So, bellows, Bourdon tubes and diaphragm gauges will find wide application in chemical process industries as pressure measuring element. These are all elastic elements. These are also called force summing device. Now, Bourdon tubes, bellows and diaphragm gauges are primarily meant for measurement of moderate pressures, but they also can be used for measurement of low pressures, but they are not suitable for measurement of very low pressure or high vacuum. Now, if you look at an indicative range, a manometer can measure up to 0.1 torr in the minimum range. Similarly, minimum range for bellows will be again about 0.1 torr, Bourdon tube may be up to 10 torr and diaphragm gauge can go further down up to 10 to the power minus 3 torr. But beyond this, we need specialized instruments. So, the purpose of this week is to know about such specialized instruments. So, for measurement of high vacuum or measurement of very low pressures, we will talk about McClure gauge, ionization gauge, thermal conductivity gauge and Knudsen gauge. In addition to that, in this week, we will also talk about differential pressure cell or DP cell, which is an important instrument for the purpose of measurement, level measurement, etc. And we will also talk about few accessories in pressure measurement, such as diaphragm seal, etc. Now, today's topic is McClure vacuum gauge. McClure vacuum gauge is essentially a modified manometer. So, look at the construction of the McClure gauge. This consists of a tube which is sealed at this end. This is a bulb and again a tube is attached. Another tube is connected and the fluid whose pressure I want to measure, that vacuum source, is attached here. So, there is a reference capillary attached here. Look at the construction. If there is a fluid such as mercury, a manometer liquid is inside, the level here and the level here will be same. Now, this tube is connected to a movable reservoir of mercury or the manometer liquid by a flexible tube or flexible hose. Please note that when the mercury level goes down this point, the branching point, and if this is connected to the vacuum source, this entire thing is now exposed to the same vacuum. So, the McClure gauge works as follows. We first adjust this level of the movable reservoir. We bring down the movable reservoir so that the mercury level here goes down and goes down this point. Let us say it comes here. Goes down the branching point. Before that, I have connected this to the vacuum source. Now, this entire volume is connected to this pressure or the vacuum. Now, I raise the movable reservoir and I raise it until the mercury level just comes here. It cuts off this part and just comes here. Then I further raise it and stop when the mercury level matches with the 0 level in the capillary. So, there are basically two steps. First, you bring down the reservoir so that this goes below the branching point, then you slowly raise it. The moment you come here, you basically get cut off from this part, and then further you slowly raise it, and then you stop when the mercury level in the reference level matches with the 0 mark. Then the reading is Y, which is the length of the fluid trapped in this tube. That is my measurement. So, basically what we did is when I raised this, when I brought it down, the mercury level went below this point. So, I had, let us say, a gas with this pressure or vacuum, then I slowly raise it and stop when this matches with the 0 mark. What I am basically doing now is I am compressing the same gas. So, the initial volume is this, final volume is this. From this, I will be able to calculate the pressure. So, let us see how. The typical range of a McClure gauge is 10 to the power minus 2 to 100 micrometer gauge or 0.001 to 10 pascals. The working principle I will repeat and is as follows. A known volume V of the gas given by the volume of the capillary, the bulb and the bottom tube up to the opening is trapped by lowering the movable reservoir down to the appropriate extent. The trapped gas of volume V is then at the vacuum P. This is what we explained. Now, the movable reservoir is slowly raised till the level of the manometer liquid in the capillary reference matches with the 0 mark on the stem. This operation compresses the trapped gas to a volume Vc and pressure Pc equivalent to the head Y indicated by the manometer as shown. So, initially I had the volume of the gas as the volume of this tube, the volume of the bulb as well as the volume of the tube up to this point, and the pressure of that gas was same as the vacuum. Now, when I raise the movable reservoir and come up to this 0 mark here, the volume of the gas in the sealed capillary is Y. So, basically I am compressed the gas of the previous volume up to this volume, and the pressure after compression is indicated by the head Y. We represent the volume of the compressed gas as Vc and the pressure of the compressed gas as Pc, which is equivalent to the head Y. Head Y indicated by the manometer in the figure. The corresponding volume of the gas is given by the volume of the capillary of Vc into A Vc equal to A into Y, where A is the area of the cross section of the capillary. If you can take the cross sectional area of this and this same. If it is A, then the volume is Vc Ay, or if the cross sectional area of this tube is A and this part is Y, so volume Vc is Ay. Since the entire process is isothermal, Boyle's law holds, and hence we can write P1 V1 equal to P2 V2 relationship. So, you will write P into V, which is the P is pressure before compression, V is the volume before compression. So, PV equal to PC into Vc, Vc we know as A into Y, and from manometer equation we can write as the head is expected as Y, Pc minus P is Y. So, you make use of Pv equal to Pc into Ay and Pc minus P equal to Y. You combine these, I will get this equation which says P equal to Ay square divided by V minus Ay. V is the volume of the gas before compression. So, that consists of volume of this capillary, volume of this bulb as well as volume of the tube up to this point. And Ay represents the volume only for this much. So, V is much greater than Y. So, this can also be approximated as Ay square divided by V. The approximation is valid if the initial volume V is much greater than the final volume Y, which is usually true. Note one thing, in this equation the pressure is expressed as Ay square by V, or P equal to Ay square divided by V minus A into Y. Now, A, Y, V all represents dimensions of the McClure gauge. So, the pressure is expressed in terms of dimensions of the McClure gauge. So, that is why McClure gauge can measure pressure very accurately. Advantages of the McClure gauge: it is independent of the gauge composition, it is independent of the gas composition. This is the point I was talking about, that the pressure is being measured in terms of dimensions of the McClure gauge. No property of the gas is present in the equation. So, the measurement is independent of the gas composition. Use the standard to calibrate other low pressures. McClure gauge can be used as standard to calibrate other low pressure gauges. There is no need to apply any corrections to the McClure gauge readings. However, there are some limitations of McClure gauge, or we can also say precautions that are to be taken. The gas must obey Boyle's law, because the key step was product of pressure and volume before compression and after compressions are equal, which is Boyle's law. So, gas must obey Boyle's law. Presence of condensable vapor causes pressure readings to be low. So, moisture traps should be provided. So, presence of condensable vapor may cause problems. The measuring tube should have small diameter, but capillary effect can produce significant uncertainty if the diameter of the tube is very small. So, the tube diameter should be small, but it should not be so small that there will be capillary effect to a significant extent. It cannot give continuous readings, because operator's help is required, operator's service is required for raising the movable reservoir, bringing it down, so on and so forth. Thus, steady state conditions must prevail for useful measurement. Let us now look at a simple problem for McClure vacuum gauge. A McClure gauge has volume of bulb as 100 centimeter cube and capillary diameter 1 millimeter. So, this diameter is 1 millimeter. Calculate the pressure indicated by the reading of 4 centimeter. So, this is the reading. So, this is the 0 mark in the reference capillary. So, we have this is that y in our previous derivation. So, we can make use of the previous equation that we have derived to calculate P. So, once again the McClure gauge has VV equal to 100 centimeter cube and a capillary diameter of 1 millimeter. We want to calculate the pressure indicated by the reading of 4 centimeter. And we also ask that if I use P equal to AY square by VV instead of P equal to AY square by VV minus AY, what error would result? Because this is an approximation to this. So, we want to know how much there will be error. So, calculate the cross sectional area of the capillary tube from the given diameter, make use of pi d square by 4 relationship and you get A as 0.785 millimeter square. y is given as 4 centimeter. So, 4 millimeter. Here VV, as the diagram shows, VV equal to 100 centimeter, and that VV is not only about the bulb, but also includes the volume of the capillary, volume of the bulb, as well as volume of the tube up to this branching point. So, VV includes this volume, volume of the bulb, as well as volume of the tube down up to branching point. So, VV equal to V in our previous equation. So, if I make use of P equal to Ay square by V, I get, after putting all the values, 0.1256 millimeter of mercury. VV is given as 100 centimeter square, everything we are talking about millimeter. So, express 100 centimeter square as 10 to the power 4 millimeter square. Now, let us use P equal to Ay square by Vv minus Ay equation. Again put the all values and you get 0.1260 millimeter of mercury. So, difference is not much. Here it is 0.1256 millimeter of mercury given by the approximate equation, and given by the original equation it is 0.1260 millimeter of mercury. So, we can find out the error as 0.1256 minus 0.1260 divided by 0.1256, which is 0.32%. So, you do not invite much error by that approximation. So, we stop our lecture 26 here.